Welcome to spectroscopy video number 2. The focus will be mass spectroscopy. Accessing prior knowledge, there are some things that will be helpful. Stoichiometry, in terms of kind of always being helpful for any scenario where we have calculations going on. Chemical structures and organic nomenclature, reminding yourself of those structures would be good. We did a little brief discussion of mass spectroscopy from topic 2 when we looked at isotopes. So maybe remembering that would be a little helpful, and we will actually even review that briefly. And then looking at empirical and molecular formula calculations and the difference between those two. And then the electromagnetic spectrum, actually that's more for the rest of spectroscopy and not so much for mass spectroscopy. The big idea is the same as the previous videos, and that won't change for the next 3 videos. And so I won't go into the details here, but the focus again today is mass spectroscopy. And here you can see a couple highlights in red where we are focusing on the massive topic of the day. So an overview of mass spectroscopy. Possibly you remember this, probably very brief overview when we did topic 2 as well. A sample is turned into a gas, if it's not already a gas, and it is heated in order to do that. And then it is ionized. And it's ionized by firing high-speed electrons at the sample. And that ionization actually does some interesting things, especially to organic compounds, which we will talk about in a little bit. The compound is then accelerated. It's an ion now, so it can be accelerated with electromagnets, and it's accelerated towards another set of electromagnets. And because these are electromagnets, they can be changed in terms of their magnetic force, if you will. So heavier particles will not deflect very much, and lighter particles will deflect more. And so when the force of the magnet is changed, the particles can range over the detector, and the detector can detect the particles and amplify them so that we can see peaks. This is an example of a mass spectrum for copper. Copper is 2 isotopes, copper 63 and copper 65, and if we know the relative heights of the peaks, we can calculate the average atomic mass. And we're not going to do that today because that's not the focus, and that's something we've already learned. But just kind of a refresher of how we looked at these mass spectra for isotopes. But now, in organic compounds, something really interesting happens. And that is these high-powered or high-speed electrons in the ionization process actually create fragments of the organic compounds. And the fragments can be really useful evidence for the structure of a compound. And that's the focus of today, is on these fragments and on breaking up the organic compound. And there are patterns for how organic compounds will break up. Here's an example. If this molecule, which is a phenyl ring, a benzene ring, with a ketone here, if this is blasted with high-speed electrons, this point here might represent a place where it would be fragmented. So we end up with a positive ion here that has a mass of 105. That means that a mass of 15 is missing, and that mass of 15 is a CH3 positive ion. So now I have 2 fragments, a fragment of 105 and a fragment of 15. So we might see the peak at 120 for the mass of the entire compound, and then we'll see a peak at 105 and a peak at 15, and that represents, the peak at 15 represents the fragment of the CH3, and the peak at 105 represents what's left over. And I think that's something to keep in mind as well, is if I have 105 plus 15, that equals the total. And this 105 and this 15 represent fragments. And so it is often the case, not 100%, for reasons we can talk about a little bit, but it is often the case that fragments are in pairs, where the 2 pairs add up to the total mass because it's just broken into 2 pieces. So here's a look at ethanol. I'd like you to consider just taking a glance at this and seeing what you can come up with without looking at the rest of your notes, and think about how ethanol might fragment. Where in this molecule might fragments break apart? And here is a look at a lot of things. Loss of H. Typically, loss of H will only occur if the H is attached to something like an oxygen, where it's a bit more exposed away from the main carbon chain. It might be a carboxylic acid. Hydrogens can be lost from any of the organic molecules, but it's much more common for it to be lost from an oxygen or even a nitrogen. So if we lose an H, that's a mass of 1, so we have 45 left over. Well, if the fragment begins here, then we have a loss of OH. OH has a mass of 17. What is 46 minus 17? That's 29. So there's no peak at 17. And you kind of go, Mr. T, why is there no peak at 17? There should be. Well, this is OH. OH tends to be a negative ion, and it's a little bit more challenging to remove electrons from that OH because of the electronegativity of the oxygen. So maybe there's no peak at 17, but there is a peak at 29, and 29 is the remaining fragment. And so by default, there is a fragment at 17 because 46 minus 29 is 17. 17 is the loss of the OH, and 29 is the remainder after the OH. And so they're both due to the loss of the OH. And this is earlier I said we might not be able to see the pair of fragments that add up to 46. Well, this fragment is missing. But maybe there's a reason for that, because the OH might not carry a negative, or might not carry a positive charge. This ion, this ethanol ion, might be split up into CH2OH plus CH3. So if the fragment is here, this is 15, this is 31. Do we see a peak at 15 for the CH3? Yes. Is here. Do we see this peak at 31? Yes, right here. Here we go. So not too bad. And the way they did this is, I'm not sure why they did 2 arrows here. If this comes off and is not an ion, maybe it doesn't show up as a peak. And this is the ion. Here we have the ion, and this is not an ion, so it doesn't show up. But between the two of these, they will be positive ions, and we will see the peak at 15, and we will see the peak at 31. 15 plus 31 is 46. 15 is commonly a CH3. 17 is commonly an OH. 29 is commonly a CH2CH3. So there are patterns to the way that the fragments will form. And those patterns are in the data booklet. And it is certainly the case that the data booklet does not contain all of the fragments. And there are some confusing factors, like 28 could be an ethene moiety, or it could be a carbonyl. 29 can be an ethyl or an aldehyde. So there are some sort of confusing things that come up where it could be two different fragments will give the same mass. But we'll learn to see the patterns, and we'll often have more than just the mass spec. We'll have an infrared spectrum, which we'll learn about in the future. We'll have an NMR spectrum, which we will also learn about in the future. So typically, mass spec is not the only form of spectroscopy that we have to tell us about a compound. So now I'm going to insert a little bit of chemical humor. Breaking up is hard to do. Ha ha, ha ha. So let's do a sample problem. A molecule with an empirical formula CH2O. And let's be clear now, this empirical formula is given to us, but we could calculate it if we were given other information, like, 52% carbon and 48% oxygen and okay, I didn't do the math. 46% oxygen, 2% hydrogen. I'm just making up numbers. But if we're given these percents, we can calculate the empirical formula. So this will be a nice way for us to review topic 1 and how to calculate empirical formulas. But here we've got an empirical formula. We have the simplified mass spectrum, and I will say, if you look at mass spectra online, they are definitely not as clean as these mass spectrum, and that's okay. We'll use what IB gives us, and we'll do our best. And occasionally we'll look at real mass spectrum, and we'll see that they're not quite as clean. Deduce the molecular formula and give a possible structure of the compound. Possible structure. Maybe there's more than one possible structure, and because this is only one spectrum, mass spec, it's harder to give an exact answer sometimes. Whereas when we start to do IR and NMR, we can narrow our focus and actually say, you know what, this is the only compound that is consistent with all of the spectra. So step 1 is to determine the molecular formula. Think about what we need in order to do that. What information do we need? And we know the empirical formula, CH2O, and so the molecular formula is going to be some multiplication factor n times the empirical formula. But the ratio of 1 to 2 to 1 will be maintained. And if we look at the spectrum, the parent ion is what I would call the full molecule, although it's not a molecule when it goes through the mass spec, it becomes an ion. The parent ion is 60. I'm going to show you some spectra later that don't have the parent ion, because the parent ion for some reason is just not stable enough. It gets fragmented too easily, and the parent ion is not present, and that makes it a little challenging sometimes. But we live with the challenge, accept it, and just accept some flexibility and ambiguity at times. But I know the mass of the parent ion. I know the full molar mass. So that means I can figure out the relative atomic mass of the empirical formula, and I call this the empirical formula mass. So the mass of the empirical formula is 30. So N is the molar mass, which came from the mass spec. And so the mass spectrum gave us the full molar mass, and this is the empirical formula mass. I just call it the EF mass. It is a relative atomic mass. 60 divided by 30 is 2. And so that means that I need to take the empirical formula, CH2O, and multiply by 2. And I end up with C2H4O2. So I know the molecular formula now. So start drawing some compounds. Like what might this look like? I mean, if I have CO and C, and can I put some H's and O's around it? If I have CC and an O, where's the other O? What am I going to need to do to make this compound? And maybe even consider looking at the index of hydrogen deficiency. How many hydrogens should it have? How many does it have? So what does that tell you about the structure? So these are things we can start considering now as we go through this process. It's like kind of figuring out a puzzle. That's why I love it. So let's look at some peaks. We've got some peaks to identify. We have a peak at 45, we have a peak at 43, and we have a peak at 15. And we're given a little bit of guidance here. 60 minus 45. 60 minus 17 makes a peak at 43, and 60 minus 15 makes a peak at 45. So these numbers, 45, 17, and 15, are just as important as the 15, the 43, and the 45. And I recognize that the 15 and the 45 already show up. But the 17 doesn't, and that can tell us something. The fact that it doesn't show up still tells us something. So be thinking about what we can do for an explanation here. Typically, CH3 is the peak at 15, and so 45, what does 45 come from? 45 could come from the COOH. And if we look at our empirical formula, the empirical formula has 2 carbons, 4 hydrogens, so 3 plus 1 is 4, and 2 oxygens. And so maybe we've got a carboxylic acid. 17 is the loss of an OH, which leaves behind C2H3O with a positive charge. And then the loss of 15 is the loss of CH3, which means the presence of that COOH. You're like, it has a positive charge. Mr. T, you said OH wouldn't be a positive charge. Well, there are other things here besides just the OH of the carboxylic acid. If this is possibly a carboxylic acid, COOH, looks like that. Well, this carbon can hold a positive charge quite easily. And so now, I just brought that back to a new page. Okay, we've got 2 carbons. If I draw 3 hydrogens here, I know I have a CH3. Loss of CH3, presence of CH3, we have lots of evidence that there is a CH3. And I have a COOH, and COOH tends to be a carboxylic acid, if I draw the full Lewis structure. So, alright, that's a possible structure. And this possible structure is consistent with the data we have thus far. And there it is. And I mentioned this earlier, but I included this just to kind of make sure I talked about it. There's no peak at 17 for the OH, but there is a peak at 43, which is the loss of the OH. So we see this is 43 and this is 17. The fact that there is no peak at 17 doesn't mean this isn't a fragment. The presence of the peak at 43 means this was lost. And it was lost probably as a neutral particle, if you will. And this was the positive ion, 43. There you go. Fun stuff. We'll do a little bit more practice in class as well. Nature of science, improvements in instrumentation have made identification and structural determination of compounds routine. There was a time when determining these structures was very challenging, very time consuming. Now it's quite easy for most compounds to figure out their structures using these techniques. Connections to other topics, we talked about using topic 1.2, or well, I just said topic 1 in general, to look at empirical formula and percentage composition data, and now we have the mass spec to determine the molecular formula. As a summary, I just like saying mass spec fragments can be used to help deduce. The word deduce here means to figure out, essentially, to figure out chemical structures. I'm using the word deduce here because that's an IB command term. So I definitely like using the command terms when possible. Mass spec fragment patterns can be used to help deduce chemical structures. Mass spec will be one piece of all the different types of spectroscopy we study. Thank you for listening. Much appreciated. In terms of submitting questions and feedback on the Google form, I will be calling this spectroscopy video 2MS for mass spectroscopy. There were no checkpoint questions for this particular video, but feel free to ask questions and or provide feedback. Thank you very much. Have a great day. See you in class.